So we're going to start with a very simple concept that you've probably seen in high school, and this is the concept of decimal expansions, and especially for rational numbers. So decimal expansions of rational numbers. And let's say that I just focus on numbers between 0 and 1, because you can easily extend this to numbers that are not between 0 and 1. So if I write something like 0 point and then some sequence of numbers. So A1, A2, so on to AN, where each AI is a digit. So each AI is either 0 or 1 or 2 all the way to 9, because we're doing decimal, we're doing it in base 10. What does this mean? Well, the meaning that I'm going to assign to this is that I'm going to say this is just A1 divided by 10 plus A2 divided by 100 plus A3 divided by 1,000, so on. So in general, I can say that this is the sum of I from 1 to n of AI over 10 to the power of I, okay? And this is called the decimal expansion. Of course, instead of having a 0 before the decimal point, I can have another integer before the decimal point, and it works in the normal way. It would just be that integer plus this. Okay. So now what happens if I have an infinite sequence? So let's say I have 0 point, and then I have A1, A2, A3, so on, but this goes on forever. And again, all of my AIs are digits, so they are in the set 0 to 9. Okay, again, I can use the same definition. I can say that I just define this to be the sum of I from 0 to infinity of AI over 10 to the power of I. And of course, this has some connections to calculus and connections to basic courses in sequences and series. I guess you covered that in analysis. But I can have a definition like this. But I'm not interested in the general case. I'm interested in the case where this gives me a rational result. Okay, so I'm going to define two types of decimal expansions. I'm going to first take this one, and I'm going to call this a terminating decimal expansion. So it's terminating because I only have a finite number of digits. Of course, after this, I can add as many zeros as I want, but at the end of the day, it's terminating. I don't really have anything after the nth digit, right? But I can also define a repeating pattern. So I have a repeating decimal expansion if my decimal expansion looks something like this. So I have 0 point, and then I have A1, A2 to AN, let's say. And then I have the same thing repeating. So after this, I have another copy of A1, A2 to AN, then another copy, and so on. And this goes on forever. So I would actually write this as 0 point A1, A2 to AN, and I will just add a bar here, which means that A1 to AN is repeating. And then I can also have a mixed version, which is that I have something like this: 0 point, let's say A1, A2 to AN, and then B1, B2 to BM. And this first part is not repeating, but the second part is repeating. So something like this, for example, if I have 0.125 repeating, what this actually means is 0.12 and then 5 forever. Okay, great. But whenever I say that I have a terminating decimal expansion, I just mean this. When I say I have a repeating decimal expansion, I mean both repeating and mixed. So I just use the word repeating for both of these. Now, of course, not every decimal expansion is terminating or repeating or a mix of terminating and repeating. For example, I can consider this. I can consider 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so on. Let's say I just write all of my natural numbers here. This is definitely not a repeating sequence. So I'm not going to look at these ones. I'm only going to look at the decimal expansions that are terminating, repeating, or a mix of terminating and repeating. And I want to say that these decimal expansions correspond exactly to the set of rational numbers. And of course, again, I'm looking at the numbers between 0 and 1, so I would only look at rational numbers between 0 and 1. So I'm going to prove two theorems. This is my first theorem. I say if x, and let's say this is again between 0 and 1, can be 0, is a terminating, repeating, or mixed decimal expansion, then this x is actually a rational number. Okay, this is pretty easy to prove. So it's just the casework. So my first case is if x is just a terminating expansion. So I have something like this. I have that x is 0.a1, a2 to an. Okay. Now, what I can do is I can just write this as a number, right? So I can just use the definition. Sorry, this one. And this definition is just giving me a sum of a finite number of rational numbers, so it's a rational number. So this x is just the sum of ai over 10 to the power of I. And it's a sum of rational numbers because my I goes from 1 to n, and it's a finite number of rational numbers, so it's a rational. Okay. If I want to explicitly write it, actually, it's like the number a1, a2 to an. I'm sorry for this slight abuse of notation, divided by 10 to the power of n. Right. So I mean, this is the decimal representation of my number. I don't mean the multiplication of a1 to an. I just mean the number whose decimal representation is a1 to an divided by 10 to the power of n. So the terminating case is pretty easy. Now, here's my second case. Let's say that I have a repeating pattern. So let's say I have this one. So this is my x. Okay, what is x times 10 to the power of n? So if I take 10 to the power of n times x, it's just going to have a representation that is like this, a1, a2 to an, and then I have the decimal point, and then I have a1, a2 to an, and this is going to repeat forever, right? So if I subtract these two, I will get that 10 to the power of n minus 1 times x is a1, a2 to an. And again, I mean this as a number, a decimal representation of a number. I don't mean it as multiplication of the a's. But then this means that x is just this number, a1, a2 to an, in decimal. Actually, maybe I can just write a 10 here to show that this is a number in decimal. Maybe I could also do it here. Divided by 10 to the power of n minus 1. And of course, each of these two are integers, so this x is going to be a rational number. Finally, the last case is super easy. Case 3 is when I have a mixture. So let's say I have this one as my x. So x is this. Well, I can write it as two parts, right? So I can write that x is 0.a1, a2 to an plus 0 point and then n zeros, and then b1, b2 to bm. And this part repeats, right? Okay. So this first one, this part is, of course, a rational number. And then I know that this one, if I multiply it by 10 to the power of n, it gets rid of these n zeros, and then it would be a rational number. So this is just that rational number divided by 10 to the power of n. So this one is also a rational number. So their sum is also a rational. Okay. So this was a very simple theorem that basically said that if I have a decimal expansion, if it's terminating or repeating or a mix of terminating and repeating, then it's modeling a rational number. But now I want to show the opposite. I want to say that if I have a rational number, then it has this kind of representation. So let's say if x equals p over q, and let's say p and q are relatively prime, and let's say that my x is between 0 and 1. Actually, I don't need the case of 0 itself. And you can easily, again, extend this to all rational numbers. So if I have this, then x has a decimal representation or a decimal expansion that is either terminating or repeating or mixed. And again, when I say mixed, I mean a mix of terminating and repeating. Okay. So we're going to do a casework again. And you've probably seen this in high school. You've seen that whether I get a terminating or repeating decimal representation is really dependent on whether I have a factor of 2 or 5 in my denominator x, right? So I'm going to do a casework. I'm going to say my first case is if, in my denominator q. So I'm going to say my first case is if GCD of q and 10 is 1. And again, I'm using 10 here because I'm writing my numbers in decimal, because I'm doing all of my calculations in base 10. Of course, you can have a similar theorem for any other base, and you would just have to use that other base here. So let's say GCD of q and 10 is 1. So what does this mean? So 10 and q are relatively prime. Therefore, by Euler's theorem, there exists some t such that 10 to the power of t is congruent to 1 modulo q, right? And actually, we know exactly what this t is. I can, instead of saying 10 to the power of t, and instead of saying there exists a t, I could just say take t to be phi of q. That's literally Euler's theorem. Okay, so instead of exists t, let's just say 10. T is the Euler's phi function applied to q. So 10 to the power of 1 is, 10 to the power of t is 1 modulo q, which means what? Which means that 10 to the power of t minus 1 is a multiple of q. So there exists some number a such that q times a is 10 to the power of t minus 1. Okay, now why do I want this? Because look, my number x was p over q. So I can write this, and by the way, this a is not 0. I can write this as p times a over q times a, but q times a is 10 to the power of t minus 1. So I can write this as p times a over 10 to the power of t minus 1. Okay, why is this useful? Because I can see that this is the sum of a geometric series, right? So I can write this one, p times a over 10 to the power of t minus 1. I can write it like this. I can say this is PA over 10 to the t plus PA over 10 to the 2t plus PA over 10 to the power of 3t and so on. Okay. And this is great because this is exactly the expansion that I was looking for. So my expansion is just 0 point, and then I write PA and I keep repeating PA. And of course, I write it in base 10 and keep repeating it. So in this case, I have a repeating expansion. Great. So now let's look at the other case. Let's say that this denominator Q actually does have 2 and 5 as its prime factors. So its GCD with 10 is not 1. And let's say it only has 2 and 5. So my second case is that Q is something of this form, 2 to the power of some alpha times 5 to the power of some beta. Okay. Now, what can I do in this case? Again, remember that my X is P over Q. Okay. So it's going to be P over 2 to the power of alpha times 5 to the power of beta. Let me just multiply this by 10 to the power of something that is bigger than both alpha and beta. So 10 to the power of alpha plus beta over 10 to the power of alpha plus beta. And let's say that I also simplify. So I simplify this part with some of this part, okay? So I'm going to get P times something, whatever remains of this part, so let's call that A, over 10 to the power of alpha plus beta. But what does this mean? This means that I have a finite decimal representation, right? Because I can just write P times A, which is a natural number in decimal, and then I'm dividing it by 10 to the power of alpha plus beta. So it means that I'm just shifting it by alpha plus beta places in my decimal representation, right? So this one is going to give me a terminating representation. It's a terminating decimal expansion. And this previous one had a repeating decimal expansion. Okay. And finally, I have one case remaining, case 3, which is that Q has one of the factors 2 and 5. So it's like 2 to the power of alpha times 5 to the power of beta. And at least one of alpha and beta is not 0 times something else. So it might have some other remaining part. Let's call that Q prime. Right? So again, I'm doing the same thing. I'm saying that X is P over Q, right? So this is P over 2 to the power of alpha times 5 to the power of beta times Q prime. Okay, what do I want to do? First of all, I know that the GCD of Q prime and 10 is 0 because I've already taken out all the powers of 2 and 5 from Q. So I know that GCD of Q prime and 10 is, sorry, not 0, 1, is 1. Okay. So I have this format here. I want to somehow get P over Q prime. So what should I do? I have X here. Let's say that I multiply X by 10 to the power of alpha plus beta. So what happens if I have 10 to the power of alpha plus beta times X? Okay. So this is again going to be 10 to the power of alpha plus beta times P over 2 to the power of alpha times 5 to the power of beta times Q prime. Okay. Again, I'm going to cancel out. I'm going to cancel this 2 to the power of alpha, 5 to the power of beta with some of the factors that I have here, not with all of them. So what I'm going to get here is that I'm going to get P times something, whatever remains of this 10 to the power of alpha plus beta. So again, let's call that A over Q prime. Okay, but this is great because look, GCD of Q prime and 10 is 1. I got a fraction that has Q prime as its denominator. So I'm back to case 1, and I know that I have a repeating expansion. So this thing, 10 to the power of alpha plus beta times X, this has a repeating expansion. Okay. So what is the expansion for X? It's just take the expansion for 10 to the power of alpha plus beta times X and shift it by alpha plus beta positions. We proved 2 theorems. We proved that if I have a terminating, repeating, or mixed decimal expansion, then that's a rational number. And if I have a rational number, then it has a terminating, repeating, or mixed expansion. And of course, again, I'm doing this for numbers between 0 and 1. You can just do it for any number. Why did I do all of this? Because basically the problem is that we have some holes in the rational numbers, right? So suppose that I write a decimal expansion. So suppose that I write x equals to something. And let's say that it's not a repeating decimal expansion. I can easily come up with a non-repeating decimal expansion, right? So I can say 0 point, and then I can just say, I don't know, write all the integers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, blah, blah, right? I can easily come up with a sequence that is not repeating. So whatever this sequence is, it's not going to be a rational number. But right now, I don't really have a meaning for this because remember, I have to define every set that I'm using. And I've so far only defined the set of rational numbers, right? So I have some holes in my rational numbers. I have things like this, which intuitively makes sense to me. I mean, sure, this is an infinite decimal expansion, but I mean, I also have some sort of a meaning for it. If I give you a rational number, you can compare it with x, right? Because you can do the comparison digit by digit. So this x has some meaning for me, but I don't really have it in any of my number sets so far. So I want to define a set of numbers that has this kind of x. And of course, that's the set of real numbers, and we're going to see it. But before going forward, I have to define some other things. So first of all, I'm going to define the concept of an order, an ordered set, and so on. So let's say I have a set A. So let A be a set. An order on A is just a relation. It's a relation. Now, here's the thing. I'm going to show it like this because I'm doing comparison. It's an order, but this is just a symbol. It's just a relation. So I could, instead of this, just use a letter of the alphabet. It's a relation R, okay, as a subset of A times A. But again, instead of calling it R, I'm just going to call it less than, okay, such that it satisfies two properties. Very easy. My first property is that I want to be able to compare any two members of my set A. So for every A and B in A, I have exactly one of the following cases. We have exactly one of these three cases. So either A is less than B, or A is equal to B, so they're the same element, or B is less than A. So I want it to be a total order, basically. I want to be able to compare any element with any other element. And then the second thing I want is transitivity. So I want to say for every A, B, C in my set, if A is less than B and B is less than C, then A is less than C. Okay. And if I have a set with an order, I call it an ordered set. And of course, based on this, I can also define another kind of order. I can say A is less than or equal to B. And whenever I say this, what I mean is that A is less than B or A is equal to B. So this is just a normal intuition that you have. Okay. But this less than equal is technically not an order with this definition. Okay. But whenever I have the strict order that says some number is strictly less than some other number, of course, I can then define the non-strict version. Okay, based on this, I want to define some other things. So we've already talked about finite sets. We've talked about sets of natural numbers. We've seen that For example, Velourdering said that if you have a non-empty subset of natural numbers, it has a minimum element. But I didn't really give you a definition of minimum, but it's a very obvious thing, right? So an element of a set is the minimum element if it's smaller than every other element in that set. Okay. But now I want to make this a little bit more complicated. I want to say this. I want to say, let U, our universe, be an ordered set. And suppose that I have a subset. So A is a subset of my universe U. Okay. I'm going to define what an upper bound means. So I would say an element, let's call it B, in U is an upper bound of A if for every element in my set A, B is bigger than that element. Okay. Or actually, I can write it in the other way around. Every element is less than or equal to B. So very intuitive definition. If I have a set of elements A, and if I have something that is greater than or equal to every element in that set, I say that's an upper bound of my set. Okay. Now, imagine this. I mean, I'm going to draw some things in this session. These are just for intuition. So my drawings don't mean anything formally. So let's say this is my set A somehow. And let's say the higher I go, the bigger the numbers get. And let's say I have a number that is bigger than everything in A. This is B. This is an upper bound of it. But now, not every upper bound is really interesting, right? I would like to have the smallest possible upper bound. So I can look at the set of all upper bounds of A, and let's call that set B. So this is B, the set B of all the upper bounds of A. And then I want to take the smallest element of this B. So I say this, I say let B be the set of all upper bounds of A. Okay, I want to take this smallest upper bound, and I want to give it a name. I'm going to call it the supremum of A. Yeah, I want to say this. I want to say if there exists some number, let's call it S, such that, first of all, S is an upper bound on A. So S is in B. Or another way of writing this is that for every A in A is less than or equal to S. Okay, but also it's the smallest upper bound. So I want to say that for every other S prime, if S prime is in B, then S prime is bigger than S. If I have an S like this, then I call S the supremum of A. Then S is the supremum of A. And I'm just going to write it like this. I'm going to say that S is the supremum. Okay. Now, I don't know if this element S is actually in A or not. So I can have cases where S is in A. I can have cases where S is not in A. I can have cases where S doesn't exist. Okay. So let's do some examples. So suppose that my universe is the natural numbers. So let U be the natural numbers. Okay. Give me an example of a set A that has a supremum, and give me an example of a set A that doesn't have a supremum.
An even subset.
Yeah. Okay. So let's say A is just the set consisting of 1, right? what is the smallest what is the smallest upper bound of A, the supremum of A? It's just 1. And as you see, it's in A itself. So in this case, actually, the supremum of A is the same as the maximum of A. And actually, that's how I can define maximum. I can say the maximum of a set is its supremum if the supremum happens to also be a member of the set. Okay. So give me a set whose supremum is not in itself. Can I have that? Give me a set that doesn't have a supremum. Yeah, I mean, any infinite sets, basically, right? So if I just take all the natural numbers, I don't even have an upper bound for this. So of course, I don't have a smallest upper bound. Okay. But let's now change our universe. So let's say my universe is rational numbers now. Again, I can have a set that has a supremum, and its supremum is its maximum. It's in the set itself. Just take the same set, A, just one number. Give me a set that has a supremum, but doesn't include its own supremum.
Number that represented 1 minus 1 away.
Yeah. Well, we can make many of these things, but let's say I take the set A of all the numbers in Q that are less than 1. Okay. The supremum of this set is 1. Very easy to check. This is literally by definition, right? The smallest number that is bigger than everything in A is just 1. But 1 is not in A itself. Okay. Now, what do I like to have? Well, sometimes I have this set A, and it doesn't have an upper bound at all. In the cases where it doesn't have an upper bound, I don't really want to talk about the supremum. But when it does have an upper bound, I would like it to also have a supremum. Okay. So I say this. I say if my universe is an ordered set, I say that U has the supremum property or the least upper bound property. Sometimes they just write it like this, least upper bound property. If every subset of U that has an upper bound also has a least upper bound as a super. If every, well, I have to say non-empty, right? Non-empty subset A of U that has an upper bound also has a supremum. Okay. So this is the least upper bound property or the supremum property. Okay. Now consider the set of natural numbers with the normal definition of order that we have on them. Does that set satisfy this requirement? So does N have the supremum property? So if I have a subset of natural numbers that is bounded from above as an upper bound, will it always have a smallest upper bound in natural numbers? Yes, why?
Because it's
Yes, well, but there is another way of looking at this as well without talking about maximum. I can say, well, suppose that A has an upper bound. So let A be bounded above. I just define B as before. So I say let B be the set of upper bounds of A. Yes, I want to use well ordering. So B is not empty, right? Because this is just by assumption, because I'm saying that A is bounded from above. So it has some bound, some upper bound. So the set of upper bounds is not empty. But any non-empty subset of natural numbers has the smallest element. So I have a supremum. And of course, in this case, the supremum is just the maximum element of A. Okay. So N has this least upper bound property. But what's interesting is that when we go from natural numbers to rational numbers, we actually lose this property. So if I ask you, does Q have the least upper bound property? The answer here is suddenly no. Okay. Can you think of a subset of Q that is bounded from above, but doesn't have a supremum, doesn't have a least upper bound? Yeah. So I can define something like this. I can say, suppose A is the set of all X in Q, such that, first of all, let's say I want to take positive numbers. And secondly, let's say that I want to say that X squared is less than or equal to 2. Okay. So intuitively, these are all the numbers that are smaller than square root of 2. Right, all the rational numbers. We don't really have real numbers, so I can't really talk about square root of 2 here. So instead, I'm just saying X squared is less than or equal to 2, because I can say this using only integers and rational numbers, right? But intuitively, you have this idea that if this set is supposed to have a supremum, the supremum is supposed to be square root of 2, but square root of 2 is not really in my universe Q. Right. Okay, how would you actually prove that this set does not have a supremum? Well, first of all, I have to show that this set has an upper bound. That's pretty easy. I can say that 3 is an upper bound. For A. So it's pretty easy to check that every element of A is less than 3. Right. But now, what you can do is you can say, suppose, for the sake of contradiction, that I do have a least upper bound. And because I'm working in Q, my least upper bound has to be a rational number. So my least upper bound should be something that I can write as P over Q. But this gets us back to the whole point that square root of 2 is not a rational number. So you can just repeat the same proof that you had for square root of 2 not being a rational number. And then given any upper bound, you can find the smaller upper bounds. Actually, after the class today, one of the students asked me to prove this, and I'm going to just give you the proof. So we want to show that this particular set A does not have a supremum in Q. We already know that A has an upper bound in Q because 3 is an upper bound in Q. So I'm just going to prove this by contradiction. I'm going to say, suppose I have some number, let's call it S in Q, which is the supremum of A, such that S is the supremum of A. I'm going to get a contradiction out of this. And the way I'm going to get a contradiction is by doing a case work over S squared. So I'm going to say, let's look at S squared. And I have 3 cases. It's either less than 2, or it's more than 2, or it's exactly 2. I'm going to get a contradiction in any case. So case 1, if S squared is less than 2. What does this mean? This means that if I look at the square of S, it's something like 2 minus epsilon for some epsilon that is greater than 0. Okay. So what I want to do in this case is I want to find some number in A that is actually bigger than S. And if I can do that, then I've shown that S is not even an upper bound of A. And so it can't be the supremum because it's not even an upper bound, right? So I want to show this. I want to show that there exists some delta greater than 0, such that S plus delta is actually in A. Okay, so this is a number that is bigger than S, and if this number is in A, then S is not an upper bound on A. But when is S plus delta in A? When I have that S plus delta squared is less than or equal to 2. This part is, of course, there. So let's see. I have S plus delta squared, and this is just going to be S squared plus delta squared plus 2S delta. 2S delta. And I want this to be less than or equal to 2. Okay, so I know that S squared is 2 minus epsilon. So I want to have 2 minus epsilon plus I have delta 2 plus 2S delta. I'm just going to factor a delta out. So delta times delta plus 2S is less than or equal to 2. Cancel the 2's, move the epsilon to the other side. You will get that delta times delta plus 2S should be less than or equal to epsilon. Okay. So here's the thing. I know that this S is at most 3 because remember 3 was an upper bound on A. And I can also choose my delta to be at most 1. So let's say I add the extra condition that delta is at most 1, and I already know that S is at most 3. So this part, delta plus 2S, is going to be at most 7. So it's enough if I just have delta times 7 less than or equal to epsilon. So I just choose a delta that is less than or equal to epsilon 7s, right? But I also need it to be less than 1 from there, so I'll just take something that is minimum of epsilon over 7 and 1. And if I choose a delta like this, then S plus delta squared is going to be less than or equal to 2, which means that S plus delta is going to be in A. And since S plus delta is bigger than S and it's in A, so S is not an upper bound of A. That's the contradiction in this case. Now I can do a different case where I say S squared is greater than 2. You see what I'm doing here? Basically, I want to say that intuitively this S, which is the supremum, has to be square root of 2, and then I want to say square root of 2 is not in Q, it's not a rational number. So, but I can't talk about square root of 2 because I can only talk about things that I can do with rational numbers. So I'm saying either S squared is less than 2, in which case I get a contradiction, or S squared is greater than 2, in which case I'm going to also get a contradiction. So because these two cases give me a contradiction, I must have that S squared is equal to 2. Okay, so this is my case 1. Let's do case 2. I need a contradiction in this case as well. I want to say in this case that S squared is actually bigger than 2. So again, it means that there exists some epsilon greater than 0 such that S squared is 2 plus epsilon. Right. And by the way, all of these epsilons and numbers that I'm using here, they're all rational. I'm not talking about real numbers at this point at all. Okay. Now, this time, I want to say that, well, S might be an upper bound, but it's not the smallest upper bound. So I'm going to find an even smaller upper bound. So I'm going to say that there exists some delta greater than 0, such that S minus delta is an upper bound on A. Now, why would this be a contradiction if I can prove it? Because S minus delta is, of course, smaller than S. And it's an upper bound on A, but S was supposed to be the smallest upper bound. S was supposed to be the supremum. So if I can find such a delta, I have my contradiction. Okay. Again, I'm going to do the same thing as before. What is S minus delta squared? It's just going to be S squared plus delta squared minus 2S delta, right? And I want this to be greater than 2. Okay. So I want to choose my delta such that this whole thing is greater than 2. Now, I know that S squared is 2 plus epsilon, so I want 2 plus epsilon plus delta squared minus 2S delta to be greater than 2. Okay. So cancel the 2's from the two sides. And let's see, I will have that epsilon is bigger than 2s delta minus delta squared. And I can just factor out the delta. So epsilon is greater than delta times 2s minus delta. Right. So in order to have this, I don't even need the minus delta here. It's enough if I have epsilon is greater than delta times 2s. And again, remember that I know my s is less than or equal to 3. So it's enough if I have epsilon bigger than 6 delta. So just choose a delta that is less than 1/6 of epsilon. So choose delta less than epsilon 6. And of course, you can do this. And then you can just do all of these computations, and you will see that s minus delta squared is greater than 2. Now, what do I know? I know that s minus delta squared is greater than 2, but also I know that for every number a in a squared is less than 2. So this means that a squared is less than s minus delta squared, which means that a is less than s minus delta. So s minus delta is an upper bound on my set A, which means that s was not the smallest upper bound, s was not the supremum. This is again a contradiction. So we've got contradictions in 2 cases. The only remaining case is if s squared is equal to 2. And the contradiction in this case is just the proof that we've seen several times in this course that says square root of 2 is not a rational number. So if I have s squared equals to 2, and remember that my s is a rational number, suppose that I can write s as p over q. So this means that p squared over q squared is 2, which means that q squared is even, right? Sorry. So 2 times q squared is p squared, so it means that p squared is even. But if p squared is even, then p is even. But if p is even, then p squared is a multiple of 4. But if p squared is a multiple of 4, q squared, which is half of p squared, is going to be a multiple of 2. So q squared is even. So q is even. But now I have that p is even and q is even. So GCD of p and q cannot be 1. Right. But I could have assumed in the beginning that I'm writing s as p over q, where the GCD is 1, because I can write every rational number there. And then I can do this, and I can show that the GCD of p and q is not 1. So this is also a contradiction. So basically, I cannot have any number s in q that serves as the supremum of this set, because I got a contradiction in every case. If s squared is less than 2, I have a contradiction. If it's greater than 2, I have a contradiction. If it's equal to 2, I also have a contradiction. Great. So Q doesn't have the least upper bound property. That's what we care about. Now, in that sense, again, Q has some holes in it. So this is going back to the same problem that I already saw with decimal expansions. So I've seen that I can write some decimal expansions, some infinite decimal expansions that are not in Q. And now I'm seeing that I have a bunch of sets in Q. I mean, this is one example, but you can create many more examples. I have a bunch of sets in Q that have upper bounds, but don't have supremums. Okay. Great. So I want to just define some other things before going to the definition of R. So basically, I want to define a set R that somehow is a superset of Q, contains Q, and I want R to have the least upper bound property. Okay. And then we will see that this is the same as saying that every decimal expansion actually leads to something. Okay, but The same way that I define supremum, I can define infimum. So I can say something like this. I can say if A is a subset of U, remember my U is like an ordered universe, then L is a lower bound for A. If for every element A of A, L is less than or equal to A. Okay. And again, this is the same intuition as before. If I have this set A, I can look at the set of all the lower bounds of A. I can call this L. And I care about the largest lower bound. And that's what I call the infimum of A. Okay. So I can say let L be the set of all lower bounds of A. If this set L has a maximum, if there exists some number L in L such that for every other L prime in L, L is bigger than L prime. Okay, then L is the infimum of A. So basically I have supremum, which is the smallest upper bound, and I have infimum, which is the largest lower bound. And again, only if it exists. I'm not guaranteeing that it will always exist. Now, based on this, I can extend this definition, or I can give a variant of this definition in the other direction as well. So see, I was saying that if I have an ordered set, I say that it has the least upper bound property. Now, instead of this, I want to say it has the largest lower bound property. Or the infimum property. If every non-empty subset that has a lower bound also has an infimum. Okay. So these two seem like different properties, right? So this one says that if I have a set and I have an upper bound, I have a least upper bound. This one is looking at the other direction. It's saying that if I have a set and I have a lower bound, I have a highest lower bound. Okay. But now the interesting thing is that if I have some ordered set U, it has any of these properties if it has the other one. So these two are actually equivalent. And I'm going to only prove one side of it because the proofs are pretty much the same. So this is my theorem. If U is an ordered set, with the least upper bound property, then U also satisfies this one, the largest lower bound property. Great. So I want to prove that U satisfies the largest lower bound property. What should I do? I should say, suppose I have some subset of U, and suppose that this subset of U has a lower bound. I want to find an infimum. Okay, so I say, let A subset of U, and of course, I want to make sure that A is non-empty, and suppose that A is bounded from below. So what I mean here is that it has some lower bounds. Again, I'm going to draw this tiny picture here. This is only for intuition. Don't really think too much about it. So I have this A, and it has some lower bound L. Okay. I want to say that there is an infimum of A. I want to say that there is a largest lower bound. So I can first say, let's look at the set of all lower bounds of A. So I take this set, let's call this set big L. So I'm going to say let L be the set of all lower bounds of A. Okay, if I want to write this formally, how do I write this? This is the set of all x's in my universe such that for every A in A, X is less than or equal to A. Okay. So I'm just taking the set of all lower bounds of my original set. Now, what do I want to prove? I want to prove that this set L has a maximum element, because I want to prove that I have a largest lower bound, an infimum. Okay. Now, first of all, I'm going to prove that this set big L has a supremum, right? And again, I'm not necessarily sure that the supremum is a maximum. The supremum would be a maximum only if it's in the set L itself. Okay, but first of all, let's look at this. I know that my set, my universe U, has the least upper bound property. What does least upper bound property mean? It means that if I give you a set that is non-empty and has an upper bound, then it has a supremum. So I have this set L. Do you agree that L is non-empty? Yes, because I was saying that my original set A was bounded below, so there was a lower bound on A, and L is the set of all lower bounds. So L is not empty. Okay, L is not empty. Is L bounded from above? Do I have an upper bound on L? Well, I know that my set A is not empty, so there is some element here. Let's call it whatever, A0, right? And this A0 is going to be an upper bound on L. That's again by definition. So for every L in L, L is less than or equal to A0. So A0 is an upper bound on L. Now I have this set L, it's non-empty, it has an upper bound, so it has a supremum. Okay, so L has a supremum, or a least upper bound. Let's give this supremum some name. I don't know what to call it. Let's call it alpha. Alpha is the supremum of L. So this point here is alpha. Alpha is the least upper bound of L, and L itself was the set of lower bounds. Okay. Now, I want to talk about this particular point, alpha. Is it in A? Is it in L? Is it in both of them? Is it in none of them? What's going on here? What I care about is actually to show that alpha is in the set L. Okay. But why should alpha be in L? Okay. So first of all, alpha is what? Alpha is an upper bound on L. That's by definition, because alpha is the smallest upper bound on L. Okay, so alpha is bigger than everything in L, bigger than or equal. Right? But every element of the set A is also bigger than or equal to every element in L. So if I look at any element A0 of A, that element is an upper bound on L. Right? But alpha is supposed to be the smallest upper bound. So whenever I take an element of A, that element of A has to be greater than or equal to alpha.
simply because that element is an upper bound of L and alpha is the smallest upper bound of L. Okay, but if every element of A is bigger than or equal to alpha, that means that alpha is a lower bound of A. But if alpha is a lower bound of A, then alpha is in L. Okay, so this is what I want to say. I want to say this. I want to say every A in A is an upper bound of L. Okay. Alpha is the supremum of L. So from this, I can get that for every element of A, alpha is less than or equal to that element. So alpha is a lower bound of A. So by definition now, alpha is in L. But this is exactly what I wanted to prove, right? What did I want to prove? I wanted to prove that L has a maximum element, right? Because I wanted to say that this set A, my original set A, has a largest lower bound. But L was the set of all lower bounds, so I just wanted to say that L has a maximum element. But I've just shown that the supremum of L is a member of L. So this supremum of L is, of course, a maximum element of L. So L has a maximum element, and that maximum element is, of course, by definition, the infimum of A. So basically, this alpha is the infimum of A. It is also the supremum of L. All of these things are the same. And alpha is also in A. Is alpha in A? It can be, maybe, maybe not. Who cares? We don't need it for it. But it's actually very easy to come up with examples where, again, this is like the examples that we had up here for supremum. I can have examples for infimum. I can have sets that contain their infimum. I can have sets that don't contain their infimum. And again, if a set contains its infimum, then the infimum is also a minimum element and all of those nice things. Okay. So we've seen that if basically we have the supremum property, then we have the infimum property. You can do the mirror image of the exact same argument, and you can show the other way around as well. So if you have the infimum property, you have the supremum. Okay, great. So far I know what I want. I want to somehow extend the set of rational numbers Q to a different set that has the supremum property. But now the question is, how do I do this? And the idea here is, again, kind of similar to what we were doing for natural numbers. So remember when I was defining the natural numbers, I was saying that the set and then the number n is the set of all the numbers that are smaller than n, right? So I had this intuition that whenever I have n, this is the set 0, 1, 2, so on to n minus 1, basically, right? So my intuition was to define every number as a set and just say that this is the set that contains all the smaller numbers. So suppose I do something similar. So again, my intuition is that I want to define, for example, the number square root 2. And I want to say that this is the set of all the natural numbers, of all the rational numbers, such that these numbers are less than or equal to square root 2. Okay, what I'm writing here doesn't make sense yet because I cannot use square root 2 in defining square root 2 itself. I'm just giving you the intuition. The intuition I want to have here is that I want to say every real number is a subset of rational numbers. And I want this subset to be exactly the rational numbers that are smaller than or equal to this real number. Well, let's exclude the equal case. Let's say all the x's that are less than square root. Okay, but if I want to define square root 2, of course, I cannot use square root 2 itself. So instead, I can write this definition something like this. I can say this is the set of all x in Q such that x squared is less than 2. Okay. Now, there are some corner cases. I want to extend this idea And I want to basically define which subsets of Q are going to be my real numbers, right? So I want to take some of the subsets of Q and I want to say these are my real numbers. But I can't talk about real numbers yet because this is the point where I'm defining them. So I have to only talk about Q. I only have Q. I only have rational numbers. Okay. So here's the idea of what we call a Dedekind cut. Another German mathematician. So let's say that I have my set Q. And again, just think of this as something on the number line. So I have Q here. And let's say this is 0. On the right side, I have all the positive rational numbers. On the left side, I have all the negative ones. What I want to do is I want to actually cut this in 2 parts, right? I want to say I have a set A on this side, and then I have a set B on this side. Okay. And what I want is for every element of B to be bigger than every element of A. Okay. And if I have this, then I want to say that this A is a cut. And I want to say that for every such A, I have a real number. So I want to take those subsets of the rational numbers such that all their complement only contains numbers that are bigger than them. Right? But I will need a little bit more than that. So I'm going to define this. I'm going to say a cut is a subset A of Q such that I have these properties. First of all, I really want to cut Q in 2 halves. So I want to make sure that A is not empty, and I want to make sure that B is not empty. So my first property is that A is not the empty set, and A is not all of my rational numbers. Okay. The second property I want to have is that basically if I have some number here in A, then I want to have everything that is smaller than it in my set A as well. Because again, my intuition is that I'm cutting the rational numbers from some point and I'm saying take everything that is smaller. Okay, so my second property is that if A is in A and A prime in Q and A prime is less than A, then A prime is also in my set. Okay. So if I have some number in my set A, I have to take all the numbers that are smaller than that in my set A as well. So if I take this number, I have to take all the rational numbers that are smaller. Okay. Again, this is going back to the idea that I want to say for natural numbers, for example, I was saying that the number n is the set of all numbers that are smaller than n. Right. So here I'm doing the same thing. But I'm saying if I take this number into my cut, then I have to take everything that is smaller than it into my cut as well. Now, the last one is that I say A does not have a maximum. Now, this last one is probably the weirdest. Now, the idea is this. Again, I'm cutting my rational numbers into 2 parts, A and B, right? So imagine that, again, I'm just using intuition here. Suppose that I want to cut it at square root of 2, okay? In this case, I don't really have a problem. I can say all the numbers that are smaller than square root of 2, and all the, so those will be the set A. And then I can say all the numbers that are bigger than square root 2 are going to be the set B, right? So if I cut at square root 2, I have exactly 1 cut. But now suppose that I'm cutting at a rational number. So suppose that I'm cutting at 5, right? Now the problem is that I can say 5 is in A or I can say 5 is in B because 5 itself is a rational number, right? So I have two different cuts at 5. I have a cut where 5 goes to the set A to the left side, or I have a cut that 5 goes to the set B. I want to have only one of them. So that's why I always say A does not have a maximum. So basically, if you're in a situation like this, give 5 to B. Don't keep it in. Okay. So this is my definition of a cut. Now, if you look at this definition of cuts, you see that, for example, the intuitive definition that I had of square root 2, which would just be the set of all rational numbers that are smaller than square root 2. That's a cut, right? It's not the empty set. It's not all of the rational numbers. If I have a number A that is smaller than square root 2 and some A prime that is smaller than A, then A prime is also smaller than square root 2, right? And it doesn't have a maximum element either. So I can define this and it makes sense. Okay. So I hope you understood the formal definition. So this is the formal definition and also the intuition, which is just I'm cutting at some point, taking all the numbers that are smaller. So here's the thing. We have a definition, real numbers are, it's just going to be the set of all cuts. It's just the set of all A's subset of Q such that A is a cut. That's my definition of real numbers. So I'm just defining the real numbers as being cut. So I'm saying every real number is just one way of cutting the rational numbers in two halves, in A and B, such that all the elements in A are smaller than all the elements in B. And I mean, in this definition, I'm not even using B, I'm just writing everything based on A. Okay.
What is the rational number that you can do not have a maximum of maximized power?
Yeah, so well, here's the thing. For example, 2 as a real number, I write a subscript here because 2 as a real number is not different than 2 as a rational number, right? What would this be? This would be the set of all the elements, so all the rational numbers A, such that A is less than 2 as a rational. But generally, I can do this for any number. So any real number is basically the same as the set of rational numbers that are smaller than it, right? But again, very importantly, I had no definition of irrational numbers before, so I couldn't just say any number is the set of rational numbers that are smaller than it, because I didn't have this kind of comparison for irrational numbers at all. Actually, I still don't have comparison on R. I have to define that. Right, I just have the set R. Okay, great. So every real number is just a cut in rational numbers. Now, here's the next one. So let's do comparison. So let A and B be real numbers. When do we say that A is smaller than B? I say that A is smaller than B if and only if A is a subset of B. Again, we're back to the same game that we had with natural numbers. Right, okay. Again, let's look at the intuition for this. The intuition is that I have different cuts of Q. So let's say this is Q. I have one cut here and everything to the left here is A. Okay, so A is a real number, but it's also a subset of Q. So everything to the left is A. And let's say I have another number B and it's cutting from here, and then everything to the left is B. So when is A less than B? Rational numbers. When A is a subset of B, when you look at them as subsets of Q. Okay. So this is how I'm defining my order on the real numbers. When I want to compare two real numbers, I just say A is less than B if and only if A is a subset. Okay. Now, you can define addition and multiplication and all those things. Let me just define addition. You can define the rest of them. So let A and B be in R. We define A plus B to be this set. I say this is the set of all X plus Y's such that X is in A and Y is in B. Okay. So again, A and B are real numbers, so each of them is a cut in rational numbers. I want to define A plus B, so I have to define a cut of rational numbers that is going to be the meaning of A plus B. I just say take any X that is in the set A, so any X that is here, and take any Y that is in the set B, any Y that is in this part here, and just add them together. Now you have to prove that this set is also a cut. So you have to prove that this set satisfies all three of these properties, because I want to define my addition in R itself. I want the addition, the sum of two real numbers to be another real number, right? But I leave it to you to check that it satisfies all of these things. Okay. What's interesting to me is this. R has the supremum property, or has the least upper bound property. Why? So remember what the least upper bound property was. What I'm saying here is that if I take a subset of real numbers, and if this subset of real numbers has an upper bound, then it has a supremum. It has a least upper bound. Okay, so let's do this. And of course, I'm talking about non-empty. I always forget to say non-empty, so non-empty sets. So let A be a non-empty subset of R bounded from above. Okay. So what does this mean? This means that there exists some bound, some upper bound B in R, such that for every A in A, B is greater than or equal to A. Okay. I want to say that there is a least upper bound. What is the least upper bound, or the supremum of A? Can you just give me a formula for this? So look, what is A? A is a set of real numbers. So it's a set of cuts. Okay. I want to define a supremum for it. I can just take the union of all these cuts. Okay. So supremum of A is just union of A. Again, let's do this. Let's say this is my Q. And let's say I have a bunch of elements in A that are cutting it. So whatever, this is A0, this is A1, this is A2, and they're all cutting it, right? So if I take the union of them, it will give me everything that is like smaller than this, union with everything that is smaller than this, union with everything that is smaller than this. And this doesn't have to be finite or countable or anything like that. So for example, let's do a simple example here. Let's say A is the set of all real numbers such that they're greater than 0 and A squared is less than or equal to 2. Okay, so if I look at the real numbers, it's like going from 0 to square root of 2. Okay, let's say less than 2 so that I don't have square root of 2 itself. Okay, so all the numbers here, everything in between these 2 points is in A. Okay, but as soon as I go from R to Q, what's happening? This number here now corresponds to a cut, which basically contains everything before it, everything smaller than it, right? So I want to find an upper bound on all of these numbers. So I want to find a cut such that this cut contains every one of these previous cuts. Okay, so it has to contain their union. But also you can see that if I just take the union of these cuts, it's going to contain all of them. And containment is the same as my comparison, right? So when I was doing order here, I was saying A is less than B as a real number if A is a subset of B when you look at them as cuts. Okay, so this is exactly what I'm trying to say here. So I want to say that supremum of A is the union of all the cuts in A. Well, first of all, I have to say that this union of all the cuts in A is an upper bound on A. So let S be the union of all the cuts in A. Now, this is pretty easy. So I say for every A in A is a subset of S, because every element of A is a cut, and S is just the union of all these cuts. So every cut is a subset of the union of cuts, right? But A is a subset of S is the same as saying that A is less than or equal to S. That was my definition for comparing real numbers. That was my order on real numbers. So S is an upper bound on A. Okay. Now let's do the opposite. Let's say I have some other upper bound. So let B be an upper bound on A. Okay, what does this mean? This means that for every A in A is less than or equal to B as a real number. Okay, but if A is less than or equal to B as a real number, we can look at them again as cuts, as sets of rational numbers, and that means that A is a subset of B. So for every A in A is a subset of B. So the union of all A's is also going to be a subset of B. So the union of all A's is a subset of B. But this union of all A's was just S. So S is a subset of B. But again, that's the definition of a number being smaller. So S is less than or equal to B. So S is the supremum.
A nice question that someone asked after the end of this session was, how do I know that this union of A is actually a cut? Because remember, we defined our set of real numbers R as just being the set of cuts. So if I'm saying that my universe is R, and if I'm saying that the supremum is this set, the union of A, then I have to show that this set is a cut. And actually, I didn't use the fact that my original set is bounded from above, and that's where I'm going to use that. So let's go back to the definition of a cut. So if I want to show that a particular set is a cut, I need to show that it's not the empty set, it's not the entirety of Q. I have to show that whenever some number is in my set, everything smaller than it is also in my set. And I have to show that it does not have a maximum. Okay, so let's do this. So I'm going to just have a small lemma here, which maybe I should have put at the beginning of my proof, which is saying that if A is a set of cuts, so a set of real numbers, again, cuts and real numbers are the same, then the union of all the cuts in A is also a cut. Okay. And again, as usual, I forgot non-empty. If A is a non-empty set of cuts, then the union is also a cut. Okay, This actually doesn't hold if you think about it. Because, for example, I can let A be just the set of all real numbers. And then the union of A would be the set of all rational numbers. And by definition, we said that a cut cannot be the set of all rational numbers. So this is the part where I actually need this assumption that it is bounded from above. So let's say A is a non-empty set of cuts that is bounded from above. Bounded from above. Then the union of A is also a cut. And again, remember, cut and real number are the same thing. Okay, so we want to prove this. I have to prove several things. Remember that I just used S to show the union of A. I have to show that S is not the empty set. So first of all, A is not the empty set. So there exists some element, some real number in A. So let's say a small a in big A. And this small a is a cut, right? So small a is a cut, which means that small a is not the empty set because the empty set is not a cut. So because the union of all a's contains small a, that means that the union of A is also not the empty set. Okay. So I showed that my set S, which I'm going to use as my supremum, is not the empty set. I have to also show that it's not the entirety of Q. Okay. So what do I know here? I know that this is bounded from above. So I would say as real numbers, let B be an upper bound on A. What does this mean? This means that for every A in A is less than or equal to B, which we said is the same as saying that A is a subset of B, because these are cuts. These are real numbers that are cuts. Okay. Okay, but if every A is a subset of B, that means that S, which is the union of all A, is also a subset of B, right? So my set S is a subset of another cut. But this is a cut, B is a cut, and by definition, cut is not the same as Q. Okay, so, or another way of writing this is that this is a strict subset of Q. It's a subset of Q and not equal to Q. So S is also a subset of Q, but not equal to Q. So S is not Q. Great. So these are the two first properties that we needed to show that S is a cut. So S is not the empty set, S is not the entirety of Q, and this is where I use the fact that S is bounded from above. Now I want to say if there is an element in S, everything smaller than it is also in S. Okay, so I'm going to say this. I'm going to say, suppose some element, some P is in S. What does this mean? S, again, is the union of A. So it means that there exists some set A in A such that P is in small a, right? But again, this A is a cut. So I know that for every Q in Q, if Q is smaller than P, then Q is also in the same cut A. But if Q is in this cut A, then Q is also in the union of my cuts, which is S. Okay, so I started with any element in S and I said whatever rational number that I take which is smaller than it is also going to be in S. So S has this property of cuts as well. Finally, I have to say that S does not have a maximum. So I can prove this by contradiction. So I can say, suppose M is the maximum element of S. Okay. And remember, when I say maximum, it means that it's an element of S and it's also larger than any other element of S. Or another way of looking at it is that it's the supremum of S, but it's also in the set S as well. Okay. So this M is in S, right? And S was the union of A. So this means that there is some set, some cut in A such that M is in A. Okay. But M was the maximum of S. So M is also the maximum in this cut A. But this is a contradiction because this cut cannot have a maximum. So this contradiction shows that my set S also doesn't have a maximum. Therefore, the set that I'm defining here, the union of all A, that I'm later using as my supremum, is actually a cut. It's a real number.
So R has the least upper bound property. Whenever you have a set of real numbers, a subset of real numbers that is bounded from above, you always have a least upper bound. And of course, combining this with the previous theorem means that whenever you have a subset of real numbers that is bounded from below, you have a largest lower bound. Okay, great. So now we go back to this one. Where is it? I had this infinite decimal expansion. So let's say I have some infinite decimal expansion. This is nothing but a cut, right? Because when I was telling you that we have some intuitive understanding of what this is, so in general, let's say I have x equals 0.A1, A2, A3, so on. It's an infinite thing. My intuition was that if someone gives me a rational number, I can compare it with x, right? So if my x is this and someone gives me a rational number, for example, gives me y, which is 0.1235, right? I can compare y with x because I can compare digit by digit. As long as there's the same, I keep going until I find the first mismatch. And then I just check which one is bigger. In this case, y is bigger, right? So if my y was something like this, 1, 2, 3, 1, then y would be smaller than x. So if I have an infinite decimal representation, I have a way of comparing any rational number with it. Because I know that any rational number gives me either a finite representation or a repeating representation. And in both cases, I can do this comparison. I can find the first digit that is different, and then I can define which one is smaller and which one is bigger. Okay, so this x is actually giving me a cut in the rational numbers because I can just define the set of all the rational numbers that are smaller than this particular x, right? So this x represents a real number. Okay. Now, one point about the representations here, a technique that we will use actually also in the next session is that I don't like terminating representations. So I don't like to write something like 0.12. Okay, so instead of this, I always prefer to write 0.119 and then just repeat them. Okay. So these two are representing the same number, and I will always use the second representation. So if I always use the second representation, I don't have to talk about terminating representations. Every representation is going to have like a fixed part and then a repeating part. Okay. And then if I do this, you can go back to the original theorems and show that every rational number has a unique representation. Okay. And then again, this whole thing makes sense. I can compare any rational number with any infinite decimal expansion. So any infinite decimal representation like this is a cut, it's a real number. So we filled out our holes in both senses. Whenever I have a set that has an upper bound, it now has a supremum. And also whenever I have an infinite representation like this, an infinite decimal representation, that also is an actual number. It's a real number.